So my name is Antonia, and this is my friend Xavier. We work for a company called GiantSwarm, and we want to talk a little bit about Kubernetes at the edge today, and we want to show it to you in action as well. So hopefully the demo is going to work. Now, first, I want to talk a little bit about what edge computing is for those who may be uninitiated on the topic. And then we want to talk about a specific project which is called KubeEdge, which we are also going to demo. And maybe later we can have a little discussion if there's time. So edge computing, what is it? According to Gartner's glossary, edge computing is part of a distributed computing topology where information processing is located close to the edge, where things and people produce or consume that information. So how does that look like in practice? You can see here in this slide a factory at the bottom, and then you can also see a couple of clouds in the sky. Now, a factory is a place where many things are produced. Among those things is also information or data in this case. And the source of this information or data is usually something like sensors, actuators, and so on. Now, we refer to these kinds of devices as IIoT devices, which IIoT is the industrial Internet of Things. So traditionally, all this data from these devices will then go up to be processed in the cloud. However, it can be quite slow to do this, can be expensive to do this. Sometimes it's also just straight up not possible to do this. And this is where we introduce this additional layer between the cloud and the device, which we refer to as the edge. You can see this here in green. As you can see, there's like a couple of machines here, some sort of servers. You have to think about the servers as being physically close to the devices that you're working with or within the same network, like the network of the factory. So why would you want to do something like this? There's a couple of reasons, actually. Here's four for you. So one reason would be latency. So for example, if your edge device is a self-driving car, you really need to make really quick decisions, right? Because you can die in an accident or something like that. Actually, about this, we had this slide, we did this talk before in Europe, and there was never actually any self-driving cars, but I've noticed that there are actually a lot of self-driving cars in the city, which is really impressive, just as a side note. In any case, the other thing that you might be concerned with is bandwidth. So if you have a lot of data, then you cannot just stream all of it to the cloud, or you don't really want to. In this case, you want to do some sort of pre-processing, and then you would proceed by sending the data to the cloud. Then you also have autonomy as a big one. So for example, some factories or other locations might be a little bit further away. So the network can be very unreliable sometimes, and you still want everything to work, obviously, even if the network is down, right? Then you have privacy. So some data you might feel a little bit sensitive about. You don't really want to put that in the cloud, or you're not allowed to put it in the cloud by some regulation, user trust reason, and so on. So let's look at some examples where edge computing is already used today a lot. There are many fields, IIoT, as I mentioned, retail, smart cities, telco, healthcare, space. This is not an exhaustive list. I think just a little bit of time ago, there was another talk here where a few different use cases of edge, KubeEdge in particular were shown, also for automotive and so on. So actually new fields are being added to this list all the time. Now we want to look into how Kubernetes fits into all this, so I'm going to pass on.
Thank you. Yeah, so we already saw what Edge is and why we need it. And now we'll take a look at why we need Kubernetes at the Edge. So running workloads at the Edge is very much different from running workloads in a data center or in the cloud. First, you might need to scale to thousands of small nodes, which are often scattered across remote locations. They are resource constrained. They might be offline for a period of time. So all these things are specifics that are not usually the case in a normal Kubernetes cluster. And regardless of that, we still need to ensure that these nodes remain patched and updated consistently. And in Kubernetes, we already address all these kind of problems with in traditional IT by being declarative. So we have a declarative API, we describe the desired states, and then the system will make it real for us. It is portable, so we can run the same applications whether we are in the cloud, on-prem, or at the edge in this case. It is automated, so instead of ourselves as humans to go and operate the actions that we want to create, we will have controllers running reconciliation loops that will do the job for us. And the good thing is that we have the same model as in a familiar Kubernetes API, whether we are in AWS or at the edge. However, vanilla Kubernetes works on the assumption that stable data center networking is a thing, which is not always the case. Think about like cars, for instance. They might go in a tunnel or something, then they might remain offline for a period of time. And we need a solution to operate in these conditions. And this is where the KubeEdge project comes into play. So this KubeEdge project was started in 2018 by Huawei. And the stated mission was to extend Kubernetes at the edge and IoT devices. So the core features are having a standard Kubernetes API, which we all know, as I mentioned, handle unreliable long-haul networking, and the management of devices, through the concept of device twins, which we will talk about in a little bit. Yeah, it's been adopted pretty well by the community already. It entered CNCF already in 2019 and graduated last year in October of 2024. That topic was mentioned in the previous talk. And I wanted to cover a couple of success stories of KubeEdge, a couple of use cases. There are a lot more than that. But the first one is the overhaul of the electronic toll collection system across 85% of China. So the old system would be regular toll plazas with employees that would collect the fare from the drivers. And these were replaced by overhead gantries equipped with cameras. And these cameras would scan the license plates and process the passengers accordingly. So that system is built on 100,000 edge nodes, so quite a scale. 500,000 edge applications running on these things. And just to put into perspective, it generates around 300 million data points every day. And it is said to have improved traffic efficiency at toll stations 10 times, and like about 2 seconds, they mentioned, for each driver. And the next one, which is pretty cool, I think, is the first cloud-native edge satellite. So the use case for this was around flood prevention and disaster mitigation. So previously, the flood happens, a satellite images the area, then the data is sent back down to Earth, and a report is compiled by a person, a human. So this is quite manual, it's quite slow. And the problem with that is that in some regions, like mountainous areas usually, you could have a cloud cover, so the photographs would be useless, but they would still be transmitted. We waste data, we waste time, and we waste efficiency, basically. We can't really afford wasting bandwidth on satellites nowadays. So in 2021, China launched the first cloud-native satellite running KubeEdge. And these satellites run a small AI model on board. So the region is imaged, then that photograph is stored on the device itself, on the satellite. The AI model would process the photograph. It will identify cloud cover, water levels, and determine whether the data is worth transmitting down to Earth. If it is, there is a larger, more powerful AI model in the ground station that will do the work that we mentioned earlier. And so the disaster response time was reduced from days to hours, and data transmission was reduced by 90%. So as the number of satellites increases going to space, this is quite significant at scale. And you can find more use cases on the public website, kubeedge.io/case studies. There are quite a few. And now we are going to move on to architecture of KubeEdge.
Right, so this is the fun part where I get to show you a bunch of diagrams. If you're looking forward to it. You might recognize this cloud edge device trifecta here from the previous slides. So on the cloud layer, I have to remark that this does not necessarily mean the cloud as in a cloud provider like AWS or something like that. This could be any Kubernetes cluster, so this could very well be on-prem, and very much often it is. Then on the cloud layer, the first component that you're going to see, by the way, this is more of a higher level overview. I'm going to go into detail after this, but the first component that you're going to see on the cloud layer is the cloud core, which is basically the single point of connection between your Kubernetes cluster and KubeEdge. So all of the communication from the Kubernetes cluster to the edge will go through this component, which is called cloud core. Then at the edge layer, you can see a similar component, which is the edge core. Now you have to imagine that one edge core runs on each edge node. So you see one here, but there could be tens of thousands of them. And again, this could be like satellites or something like that. Now, the edge nodes join the Kubernetes cluster by connecting to the cloud core. And they will look like normal Kubernetes nodes if you list them. They have a special label on them, so you can schedule your workloads, but overall, it's kind of the same experience. The edge core is installed as a single binary on the machine. Now, the edge core talks to the device layer via MQTT protocol, and it can also talk to local applications via HTTP. And then on the device layer, you can see actual devices. So again, as mentioned, these can be sensors or robots or cameras or something else. Obviously, they will use their own protocols as well. And KubeEdge offers a framework that you can use to represent these kinds of devices as Kubernetes custom resources. And also in the slide, I've at least tried to mark all the Kubernetes API related streams in blue and the ones that are related to devices in red. So hopefully the next few slides can be a little bit easier to read like that. So now let's look at the cloud core in a little bit more detail. The cloud core is installed on your Kubernetes cluster via a Helm chart. You can use an upstream CLI tool that is called KeyADM to do this, for example, among other things. The cloud core has a couple of components. The first component you can see here is the Cloud Hub, which is something like the messaging broker. So this actually opens a secure, persistent channel to each edge hub, and the communication is via WebSocket or even QUIC protocol. And the Cloud Hub also has, or the Cloud Core, excuse me, also has a few controllers. You can see two here. The one is the edge controller, which propagates changes to workloads running at the edge from the Kubernetes API to the edge. And in the opposite direction, it will report things back, such as like statuses and events and so on, so from the edge to the Kubernetes API. Then the device controller, that's the red one, reconciles device CRs, the custom resources I mentioned earlier. And this syncs between Kubernetes custom resource and managed devices that you might have. And bundling this communication through the Cloud Core has a couple of benefits. So one benefit that you get is load reduction by aggregating updates. And what this means is that you don't actually get all of the updates, but instead the similar ones are going to be aggregated, so you don't overload your Kubernetes API as much. And then you also get resilience across flaky networks by doing incremental updates. And what this means is that in case your node disconnects for some time, and then later on it will reconnect, it does not actually send all of these updates at once, but it's going to do so incrementally, again, to not overload the Kubernetes API. And by doing this, you can integrate Edge into any existing Kubernetes cluster, and it has been shown that up to 100,000 Edge nodes could be added to a Kubernetes cluster like that. Now let's look at the Edge core, which is running on your Edge nodes. The Edge core has an Edge hub as well. So this is the counterpart to the Cloud Hub, and it is basically the link from the Edge to the cloud. So this, as I mentioned before, connects via WebSocket or QUIC, and it will also route all the communication from the cloud to the correct Edge modules, of which there are a few which I'm going to talk about in a moment. Also, again, this will report back things like the node and device status to the Kubernetes API. It also takes care of such stuff like keep alive and routing messages within the Edge node. Then there's two important modules here that both work with the local state, which is, the first one is the meta manager, and this is a cache and message processor. So this will store data like pod state, config map contents, and so on in a lightweight SQLite database. And this is a local database, so it basically enables the Edge node to still function when it's offline, and then it's also going to sync any changes later when it gets reconnected to the cloud. The other one that you see here is the device twin, which keeps track of the state of devices, and it manages their attributes and their status. And again, this will sync information to the cloud, but it will also sync information to any apps or other things that you run locally. Then you can see here this component called HD. And HD is something like the kubelet of the Edge core. So this will manage the lifecycle of pods, and it will talk to the container runtime. So you can actually run workloads on the Edge node just like you can in the cloud, pretty much. This also handles other resources such as config maps and secrets that are cached locally. And all of the communication at the Edge goes to this, through this messaging layer that is unique to KubeEdge, which is called Beehive. On top of that, you also get two buses. The first one is the event bus, which integrates with MQTT. And then, well, this connects Edge modules and device mappers, which we're going to talk about in a moment. And then the service bus, which provides HTTP communication with local apps and APIs. You can see here probably also, it's a little hard to see from here, but you can see that there's a container runtime, which obviously will run pods, and it will do so under the control of HD. And then you can see the mappers. The mappers translate between device protocols and KubeEdge. And all of these components together will allow the Edge node to keep running workloads and manage devices even when the network is very unstable. Now, let's talk about devices a little bit more. I'm actually going to hand over.
All right, so here we talked about how to get Edge nodes as nodes in our Kubernetes cluster. So at this point, we have a Kubernetes cluster in the cloud or wherever, and we have Edge devices, NVIDIA Jetson Nanos, Raspberry Pis, which are members of our Kubernetes cluster. So this is already a valid use case for KubeEdge, meaning you can already schedule workloads there. This is great. But we can go a bit further and manage the IoT capabilities of KubeEdge. And this is where we get into the device territory. So here it's all about protocols. So I'm talking about communication protocols to standardize how data is collected, transmitted, and exposed. So an IoT device is basically just a thing that generates data. So you get various sources like sensors, cameras, and this data is exposed on a specific protocol, so Modbus, OPC UA, these icons that you see on screen. Think like an IKEA temperature sensor connected via Zigbee to like your Home Assistant instance. This is the same idea, except we want that data to go into our KubeEdge environment. And this is where the mappers come into play. So the mappers, I'll go real quick over these. These are just translators between our hardware data and our KubeEdge world. So this is a container that runs on our edge device. And it will translate. It will have maybe like a Zigbee communicator or a Zigbee dongle or some other hardware device to be able to leverage specific data. And it will convey it to KubeEdge via this messaging protocol that we mentioned. So you can see on the screen here in a bit more visual way. So on the right-hand side, you have these hardware devices that generate specific data, not relevant which one. And on the left-hand side, we have the Kubernetes, KubeEdge environments. And the middle, the mapper, is these containers that run that specific logic that understands the protocol and understands as well how to convey that data to KubeEdge. So there are already a few of these available online in the repo. The upstream repo, but you can also build your own. There is a mapper framework, to build your own mappers. It's based on Go. So fairly good documentation around that. And to talk about how to get those devices into KubeEdge, we will work with custom resource definitions. So there are a few other custom resource definitions here. I only talk about device models and device instances. So the device model is like the kind of type of device that we want to work with, for instance, like a Philips Hue model XYZ, and the instance is the actual thing that you will deploy in your factory floor, for instance. So your factory floor being your home, Philips Hue XYZ in your living room. So this is the kind of device model, device instance concept. And we have a bit more industrial example here on screen with this blue device, an Adam 6017. I don't know these things. I haven't seen any in real life myself. But this is a fairly simple example, as in it has 8 channels, which are mapped to Modbus registers, and you can connect sensors to each of these channels. And this custom resource is what we would create if we wanted this device inside our Kubernetes cluster in KubeEdge. So here you can see this is the device model. So we have a protocol set for Modbus. We have various fields like the properties. We have one for each channel, and on the right-hand side, we have an extract from the user guide that you can find online from the vendor of this specific device. And these are the Modbus register addresses on the right, like 40,000 something. And we'll see on the device instance that once we create it, we can map each of these Modbus register addresses to our properties. And we also have the config data on how to access that device on IP and port. But I think you guys came for a demo, so let's try to look into this and make it happen. So that demo is fairly simple here. We're working with a Raspberry Pi. It is here, it's all live. There's a camera, there's like RG45 cables. So what we're going to do is we're going to count hands. So I'll talk a little bit more about that, but here I have a screenshot of the visual of what the app does. So I just wanted to do this because we are working with containers, so we don't have any visual feedback here. But this is what the app running on the Kubernetes edge device sees. So you can see we have the Raspberry Pi, we have a USB webcam, and a Python app that runs an application built with MediaPipe. So it's a framework by Google that allows you to detect like different hand postures, like facial recognition, and like body postures. This is what we use here. So we extrapolate a shoulder line, and any hand detected above the shoulder line will be counted as raised. And as you can see here on screen, we have 2 raised hands. However, the caveat here is that we have many shoulder lines here. So this is not really going to work with a large audience and with a consumer-grade webcam either. So usually we work with the front row, but there's not much of a front row. So I'm going to use Antonia as our front row.
Okay.
And she's going to be our guinea pig today. So let's bring up some dashboard. So you can see here we have a Grafana dashboard with a big 0. Our webcam is on, as you can see. And hopefully, if I point it at Antonia, so there is a bit of delay. I will explain why in a bit. we should have a change of number. We have a 1. We might have a 2 now.
Maybe. Yep.
OK, we have a 2. So as you can see, we have a change of values when we raise a hand. Now, to get into a bit more of what is going on behind the scenes, I'm going to bring up the terminal real quick. I won't spend too much time on this, but I might need to zoom in. So I hope I'm writing because I can't see what I'm doing.
Make it a little bit bigger.
Yeah, I'm going to zoom. OK, so on the top left-hand side, we have the actual KubeEdge custom resource in our cluster. So when that line will change color, it will mean that that value changed. At the bottom, we have the logs of the mapper, and at the top right, we are directly subscribed to the MQTT mapper. So we actually use an MQTT client. So now,
does it change? It does.
Yes,
okay.
It did change.
Good.
Right, so you can see what's going on here. We have the mapper, which is picking up the change of value. We have, at the top left-hand side, we have the KubeEdge device that picks up the new value as well. There is a difference in latency between these because there is this thing of KubeEdge doing that logic in the background of sending the data. And here we are querying the Kubernetes API. So it has to go to the edge core, then the cloud core, and then Kubernetes. So that's why that delay is going on here. So we don't have that much more time, so let's move on to the setup itself. So this is what is going on here. This is what we have built. So at the top, so by the way, that QR code is the repo. If you want to check it out, you will find the MQTT mapper, the custom resources, and the Python app running MediaPipe. So at the top, we have the cloud layer, as you saw before. This is our CAN cluster running on my laptop. This is representing the cloud or on-premise Kubernetes cluster to which we are joining with KubeEdge. In the middle, we have the edge layer with that Raspberry Pi here. It also has the MQTT mapper and the broker. And at the bottom, we have the device. In our case, this would be the combination of the webcam and the Python app. Now, this is kind of how we describe the device, but in real life, it would be more like an actual IP camera using a protocol like OnVIF. For instance, one of our customers uses something like that to detect holes in their paper lines. So they produce paper, and when there's a hole like this, they use this kind of recognition. And instead of counting hands, they do something much more useful like that. And the mapper section here is very simple. So this container, this mapper, subscribes to a specific MQTT topic on the MQTT broker. Whenever the Python app picks up a new raised hand, it will publish a message to the MQTT broker on that specific topic. So the mapper picks it up, updates the device CR in KubeEdge, and exposes that data on a metrics endpoint. That metrics endpoint will be scraped by our Prometheus instance, which will visualize it with Grafana. This is not the right way to do things. Don't do this. This is just for the sake of that demo. But in real life, you would more likely push that data from the mapper to like a time series database, which would be consumed by a proper IoT application. So there are better ways to do this, but this is kind of the cheap USB webcam way of making this happen and making it visual. Thank you very much. So it was a fairly simple demo, but we hope that it demonstrated a real-life industrial solution with all its layers. So this is the point of the edge to keep critical processing at the edge for low latency and resilience. And we still sync data to the cloud in our Kubernetes cluster via the device twin model. So thank you for taking the time. Thank you, Antonia, for raising your hand. And if you have any questions, feel free to go ahead. But if we don't have time, you can catch us at the end.
Thank you. So can KubeEdge be used for other cases than IoT?
Well, sure. Like the point of KubeEdge is to connect devices to a Kubernetes cluster. So having it doesn't have to be low resources or resource constrained device. It could be anything but the point of it is that it has a very different way of accessing your Kubernetes API. So a traditional kubelet would directly hit the Kubernetes API, and then you are kind of rely on your network resiliency. However, KubeEdge kind of allows you to do this in a more flexible way. And like that mapper section that I showed with the device, you don't have to use that. It's still pretty new as well. There's not a lot of customers that use it yet. But it's more about joining nodes to a Kubernetes cluster. So yes, you can do this even if it's not IoT, for sure.
Yeah.
So, have you looked into the overhead of these KubeEdge edge core installed at the edge?
Okay, so what is the overhead of these of KubeEdge in these edge devices, right?
Yes.
In terms of resources.
Yes.
Yeah. So the default marketed overhead that we get on the edge core and KubeEdge would be 70 megabytes, but benchmarks show a bit more than that, a bit over 100 megabytes. But it is fairly low resources. Memory, yes. K3s might be slightly lower, but it's a different, it's not really a comparison apples to apples.
In the demo setup there, where do you install the edge core?
So the edge core is installed on the Raspberry Pi. So you install it, you have to, basically, when you install the edge core on your edge device, you use a token that you get from the Cloud Core to basically join the device into your Kubernetes cluster.
So both the device setup and the edge core setup is in the Raspberry Pi?
Yeah, so you initially bootstrap your edge device with an OS. So this one uses Raspberry Pi OS. And then you install that edge core binary. And there's a CLI tool called KADM. And you install that binary by using that join token that you can get from the Cloud Core. So if you look into your Kubernetes cluster, there will be a secret which contains that token, for instance. You take that token, you join your cluster. It will install that binary and then create that link. So you don't actually need to open firewall ports from the cloud to the edge. It's all outbound. Yeah.
So from a Kubernetes,
Sure, go ahead.
from having a Kubernetes cluster, what you need to apply edge core, Cloud Core is a Helm chart.
Yeah.
And then the rest is the devices and edge cores.
Yes, so we install the Helm chart for the Cloud Core in the Kubernetes cluster, and then the edge nodes will have the edge core, which will talk to the Cloud Core, and then this guy will talk to the Kubernetes API and create the nodes and update the API and etcd, etc.
The Cloud Core, the Kubernetes cluster that is installed, when the Cloud Core is installed, KubeADM is used to create that cluster?
So the question is KubeADM used to bootstrap the nodes? Do you want to respond to that?
No, it does not use KubeADM for that.
It uses the KubeADM, the replacement of KubeADM would be like the Cloud Hub, the Cloud Core part. So when you don't install KubeADM on the edge nodes, you only install that one binary. It's kind of like K3s. If you use K3s, you don't use KubeADM. K3s has a join token that you join to your agents to your master. Here it's kind of the same concept, like you install that binary with a token, and the bootstrapping will be just that one binary that will run all the components. So you won't see containers and all these things.
Yeah, so the difference would be that in case of KubeEdge, your cluster can still be KubeADM based, so you could have a cluster API cluster using KubeADM, which we do, for example, at GiantsForm, but you can join the edge nodes which do not use any of that to that existing Kubernetes cluster, and then in case of K3s, you would still have the whole control plane nodes and so on, which would all be using K3s.
It's a different bootstrap mechanism.
Yeah. Yep.
Sorry, I can't hear you.
Yeah.
I would like to know if the map is like a digital twin, where you can see the virtual representation of
Okay,
the
so
physical.
the digital twin in this case would not be the mapper. So the mapper is actually a component that translates from your device protocol to MQTT. And then what you could call a digital twin would be the Kubernetes custom resource that you have for this device, which Xavier has shown earlier, where you could see the device status. So depending on what your device does and what you, which fields you have in this custom resource, you would then be able to use it as a digital twin, as a representation of your device.
Yeah.
All right, we didn't show the
Yeah.
CR, all right.
So if you look here, this is the custom resource. This is the device custom resource of the CRD installed by KubeEdge, by the Helm chart. And you can see, I can't tell from here, I'm sorry, but somewhere on there, something says twin status, and this will be the device twin. So we have a CR representation of that device, and that value will change here when we raise our hands, and yeah.
Hi, so you said like, the edge core is joining the cloud components as a worker node.
Yeah.
And so when the disconnect happens, like, do your edge core components also like get killed because you do not have a line of sight to the API server? And so how do you keep disconnected mode working where the edge core and the devices need to still have communication?
Yeah, so obviously if it's disconnected, you're not going to get any new updates through the Kubernetes API, right? But however, the node will still keep running the workload, so the container runtime is still going to be running your workloads, and also because it has the local database, it's going to save its own state, and then later when it reconnects, then you can also see these updates through the Kubernetes API again. But obviously, while it's disconnected, you're not going to have any view on what is happening.
There's a SQLite database on the side that holds the status of your desired state.
And where do you store this CR and secret, like that I see for HED? Is that a edge version of a etcd, or like you store it somewhere else?
So
This is the SQLite database that contains all these desired states. So the etcd is still in the cloud. This is the Kubernetes API, but here in this case, the edge core is talking to that local database.
yeah, so basically there's a sync process happening, so you still get to keep the status of the secret in etcd. However, there is a copy of it on the local database, and then later it gets updated if there were any changes. In case of the secret, probably not necessarily, but if any resource on the edge has changed, it's going to be updated later. So it's basically like a copy.
All right, I think we are done with questions.
I guess.
Thank you very much.
Thank you so much.